Okay, in this section we're going to go over parts 8.1 and 8.2, which is all about the properties as well as to find out, or how to find out, the pH of strong acids, strong bases, weak acids, and weak bases. So we'll start with strong acids in this case. The thing to remember about strong acids as well as strong bases is that they ionize 100% or they dissociate 100% when they hit solution. This means they will break up completely into their separate ions, and there's two different ways you can show that. Let's take, for instance, hydrochloric acid, which is a strong acid, and we'll show it breaking up in its reaction with water, and then we'll show net ionic with just its ions. In a reaction with water, it will produce the H3O plus hydronium ion, as well as the conjugate base Cl minus. If you just want to show that with pure ions, then you would show everything without the water. Just keep the HCl there, show it breaking up into H+, which is the conjugate acid, and then the conjugate base, which would be Cl-. Both of these equations mean the same thing. The thing to keep in mind here is that it's a one-way arrow. And we show it as a one-way arrow to signify or symbolize that it's a 100% dissociation. It goes totally to the products. For their Ka values, the Ka values for strong acids are large. And a large Ka value means that Ka is going to be greater than 1. We typically will not pay too much attention to the Ka of strong acids because they're so large and because they go to completion or dissociate 100%. Now, to find the pH of a strong acid, you need to use the equation pH is equal to the negative log of H+, or you can use the equation pH is equal to the negative log of H3O+. They both mean the same thing. And essentially all you need to do is figure out, well, what is the molarity of that acid, take the negative log of that molarity, because the molarity will be equal to the H+ concentration of the acid, and I'm going to show that in the following problem. So let's take a look at this problem down here. What is the pH of a 2 molar perchloric acid HClO4 solution? Perchloric acid is a strong acid, and remember, you have to have the strong acids and strong bases memorized. So the way I like to solve these problems is I first start off with the acid, and I like to show it broken down into its conjugates. Because this is a strong acid, I'll only use one arrow. And the conjugates are going to be H+, and then the perchlorate anion. And these are all aqueous, by the way. Now, the original concentration of the acid was 2 molar, 2.00 molar. This means when it dissociates 100%, it will also give 2 molar H+ ions and 2 molar perchlorate anions. Now, we want the pH, so we are just going to focus on this part right here. Now that we know how much H+ is in solution, we can use the equation pH is equal to the negative log of H+ to solve. Just plug in the number. And if we solve for this, take the log of that, but that's the positive log, so we need the negative log. Multiply by -1. The pH is going to be negative 0.30. And remember, pH does not have any units, and so that's the final answer there. And now remember, the only reason that we can use this formula straight away from the concentration of the acid is because perchloric acid is a strong acid and will dissociate 100% into its ions. So whatever the concentration of the original acid is will also be the same concentration of the H+ ions. For strong bases, the idea is very much the same. Strong bases dissociate 100% in solution, but they dissociate into OH- ions instead of H+ ions, because that's what bases do. And again, you can show that in two ways, either its reaction with water, or its net ionic, just broken up into the separate ions. And for strong bases, instead of using a Ka, we have to use a Kb, or the base dissociation constant. And just like with strong acids, the Kb for a strong base will be large, so Kb will be greater than 1. But when looking for the pH of a strong base, we cannot just take the negative log of its OH- ions and call that pH, because pH is equal to the negative log of H+ concentrations. Instead, what we must do is we have to find the pOH first. And the pOH is the negative log of the concentration of OH- ions. Once we know what the pOH is, we can then use the relationship pH plus pOH is equal to 14 to solve for the pH. Now, we typically don't use pOH when analyzing solutions or doing things in lab. pH is the kind of the go-to thing. So we often want to know pH instead of pOH, even for the case of bases. So what is the pH of a 0.35 molar solution of KOH, or potassium hydroxide? Potassium hydroxide is a strong base. And so when it is aqueous, it's going to break up into K+ and OH-. Now what we can do is we can take the original concentration of the base, which was 0.35 molar, and because this dissociates 100%, the original concentration of the base is also going to be the concentration of its ions in solution. And right here is our focus. We need to get the pOH, which is the negative log of the concentration of H or OH- ions. So let's go ahead and take that negative log. And so it looks like the pOH in this case is going to be 0.46, rounding to 2 significant figures after the decimal. Now, a lot of students are going to stop here and try and box that answer, but we're not done yet. The question asked for the pH of the solution, not the pOH. So we need to use this second relationship up here. pH is equal to pH plus pOH is equal to 14 to get the pH. Now, if I manipulate this equation algebraically, this means that pH is equal to 14 minus the pOH. Or in this case, pH will be equal to 14 minus 0.46. I'll do that into the calculator. .54 is the pH of the solution. So whenever you need to find the pH of a strong base, it's a little bit of an extra step. Because know that strong bases don't give off H plus ions, they give off OH minus ions. So you have to find the POH, and then once you have that, you can get the pH from the relationship pH plus POH is equal to 14. So go ahead and try the example problems that proceed on the Nearpod assignment, and then in the next 2 videos we'll go over weak acids and weak bases.